Long-context LLMs are hitting a hard wall, the KV cache. Memory footprint and decoding latency scale linearly with sequence length. While KV cache eviction is the standard mitigation in grouped query attention models, current methods suffer from a critical flaw. The problem is head heterogeneity. GQA architectures contain streaming heads that exclusively attend to the prompt's boundaries. Existing eviction strategies aggregate attention scores across heads, allowing these streaming heads to dominate the eviction decision. The result is the eviction of critical mid-context tokens, which destroys retrieval accuracy on long documents. CompressKV solves this by identifying semantic retrieval heads. We observe that specific heads capture semantic evidence across answer spans, not just boundary streaming. CompressKV uses a calibration dataset to score heads by aggregating attention mass over answer spans. This span aggregation standard identifies heads that attend to semantic context, even when they lack sharp top K peaks on individual tokens. These semantic retrieval heads drive token selection. For each layer, we select the top K SRHs and share their selected token indices across all heads in the GQA group. This ensures crucial mid-context evidence is retained, preventing suppression by streaming heads. Additionally, CompressKV introduces error-aware, layer-adaptive allocation. We compute the offline Frobenius norm of the difference between attention outputs with full versus compressed caches. This quantifies the compression error per layer. We then allocate the cache budget proportionally to these error estimates, prioritizing layers sensitive to compression, with zero online overhead. Results are significant. On long bench, CompressKV retains over 97% of full cache performance using just 3% of the KV budget. On needle in a haystack, it achieves 90% accuracy with only 0.7% storage. It consistently outperforms SnapKV, Cake, and HeadKV across Llama 3.1 and Mistral models. CompressKV demonstrates that modeling head functionality and leveraging offline error profiling is essential for resource-efficient long-context inference. Check the description for the paper and code.